So are there any questions? Okay. Mm-hmm. It would be good if it would be in the constructor as well as in the casting operators. So you can have an operator to cast from a boolean to it. So that's where you use the constructor, and then you can have a casting operator. You can cast from our type to a boolean, and we would want this to work as well. So yeah, let's write a short example. Let me start some screen sharing. Nope, which one was it? This one. Bildschirm freigeben. Is that the right screen? Team. Bildschirm freigeben. Nummer 4. 4. Okay, now it's the right screen. So let's start a quick demo. So if we somewhere have we won't be able to do something like this. And this you get by implementing this operator. And we want it to be explicit since we don't want the compiler to take the detour through this for other types of conversions. Anything else? You need to compare the content. So because like if you assign, for example, 1 and 2 to two variants, and then compare if the first variant is equal to the second variant, then you would expect the operation to be mathematically correct. So so if the types if the types are different within numeric types, you should just always cast to the longer type and then make a comparison. So if you have an uint8 and uint32 and you want to compare those two to each other, then you should cast the uint8 on a uint32 and then compare the values. There is a, let's say, cheap way around that, or rather a cheap way to implement this functionality, also probably satisfactory. That would be if you just compare the memory and compare it to the shorter length. So you just compare the shorter part. But the problem then is that if you have higher bit set, then it might say that it is the same, but it will not be the same in reality. So it's really better to cast it to the longer type, even if it needs more code to do so. Okay, anything else? Can you show that? I can stop screen sharing, then you can share your screen and show what error are you getting. Okay. Sorry again. No, that should be enabled. Try again. Okay. But you want to make a virtual operator? Okay. Wait. I see. I see. I see. You should write virtual before C variant object. I think I might forgot that in the reference. Now it should not longer complain. Yep. Okay, that was it. So I showed last time in the string example how to make this copy on write. So when you have a variable and you just read the value, it doesn't do anything. And then if you assign this variable to another variable and another variable, they share an internal state. So you don't need to copy every time the whole content of your string in that case when you're just assigning. But once then you decide to change one of the 3 strings that you have now, so you try to write on it, only then it will actually make a copy from the shared object such that it gets a unique individual copy for its own use, and then it modifies that. That is what's a copy on write. It makes the copy only once it decides that it needs to write to something. Mm-hmm. Wait. MyString. So let me open the MyString quickly and share the screen. Everyone sees what we're talking about. This one. It's a copy constructor, so it makes a copy. So if you initialize a variable, let's find we have use it somewhere. For example, here. In this case, it will use the copy constructor to make basically a copy of the MyString as MyString1. And the way this works is first it calls the constructor which doesn't do anything but setting the pointer to null. We could also have just set pointer to null by manually, so technically this is equivalent to just doing that, but it looks more elegant. Plus we might in this class it doesn't matter, but if we would have something more complex, so like more than one variable, it would be elegant to have like a basic constructor with no arguments that does all the initialization and then just calling it from our other constructors. And then here what we are doing is we are attaching the internal data object from the already existing instance to our own object, such that we really share the state with the other one from which we make the copy. Yes. Yeah. There is also another notation which might be more intuitive, like this. Because Well, it depends how the compiler optimizes it. So if you write it this way, you know that it will definitely take the copy constructor. If you write it this way, the compiler may choose to first just do this, and then where's our assignment, and then do that. But internally that's also very similar. So first we just initialize to null, and then we just make attach. So performance-wise, it would not make a large difference what the compiler does, but ideally it should, when assigning in this specific case, just simplify the expression to this. I think it is, but it will depend on the compiler setting. We can just, it's quite easy. You just make a breakpoint, you run it. And then we can just go to the assembly view and step by step. Wait, what was that? Okay, that is interesting. That is something that I think this is something related to one of the options I have not disabled. Let me quickly check. Link input. No, sorry. It's code generation. Yeah, I have this runtime checks on, so this will be doing some additional stuff that is not needed. But if we ignore this auto class init2, whatever the compiler added here, if we just then step further, we see that we end up directly still in this constructor. So the compiler in our case is smart enough to see that if we assign to an object which we just defined, that it doesn't make sense to first define the object and then do the assignment, that it can be done in one go with the copy constructor, and then it does that. So just as said, for demo we can here again. What do we need to disable? A lot of things. We need to disable this and code generation and that and that, and one more thing, this one. Okay, now if we run it again, it will be much more simpler in the assembly. As you see now, it's just this one call to the constructor, and it also did not include any jump tables anywhere in between, so it's much less code. And of course, if you would select a release build, then most of those wasteful presets would not be on by default. But in a debug build, the standard is to rather add as much debug code that will help you find issues as possible. So much about that. Any more questions?
No, I think so.
Okay. Anyone else with questions? Mm-hmm.
So we get this implemented, or is this from a library? And what does it do exactly? The attach?
This one.
Yeah.
Yeah, if you press F12, it brings you to the definition, and you see that we implemented it here. And what it does is quite simple. First of all, it detaches whatever might be attached, so that we have the M pointer being null and not pointing to anything, and then it sees whether we are actually attaching an object, because we could also maybe have a null object here. So if we have something, then it increments the counter on this object, ensuring that we will have we will keep track of how many objects are using this internal object, and then it just assigns the counter, the object to our own variable after it has incremented the counter. And detach is simply the opposite. First it checks whether we actually have something, and if we have something, it decrements the counter by 1. And here what this fetch and subtract does is it's an atomic operation, so it will it cannot be interrupted by another process running in parallel, and it does the subtraction, but what it returns is the initial value what the variable was before the operation. So we check if it returned 1, it means that now it's 0 because we subtracted 1 from 1, so we know that we now are like the last object which refers to this internal structure, and then we can remove it from memory. And in any case, we then set our own pointer to null. So if this the result would have been, for example, 2 or 3 or whatever, then we would not delete anything because we know how other objects are still using it. But since we are detaching, we are not longer using it. The subtract was already done. So for us, the only thing left to do is to set our own pointer to 0.
I'm so sorry, this was a little bit fast. So the fetch add, the fetch sub, that's something we have implemented within Lossworld.
No, fetch add and fetch sub are, so we use this ref counter. This is from the standard template library. So it's a template for a type atomic to which you can give different machine types, and it will implement for you for the platform on which you are this fetch add and fetch subtract operations. This one and this one.
Okay, thank you.
And yeah. What do you mean add more than one? Well, fetch and add is so this is equivalent to, well, it's not really equivalent, but it's like this. So we can increment it to 100 or to however much we want. It's just it's just an increment call. Well, it keeps no, it's not a history. It's an actual living state, so to say. So what it does is it tells you how many objects are currently using this internal structure. So we have our internal structure called sdata, and whenever we create a new string, we either are assigning some new sdata to it, or we are assigning an sdata to it that was already created for another string. So multiple instances of our CMY string can share the same sdata internal structure.
So it is over more than one instance.
Yes, exactly. And this is what makes the performance so good with this sort of implementation, because every time you would we have an example somewhere here, for example, like here where you are passing a instance of a class as by value, so not by reference like done in this case, but here where it's done really by value. Without this mechanics, you would need to create a new sdata object, allocate a lot of memory for it, copy the data. So it's a lot of computational complexity that you have. But if we use such a shared object, the whole thing is just as simple as incrementing a atomic variable and assigning a pointer, and that's it. Any more questions? Okay, so if there are no more questions, then we can proceed with the lecture. So what we will be doing today is just taking a look on some of the homework that was scheduled from the start of the lecture, and provide some reference solutions how to make those things work in a simple enough way. So let's see what was the first homework. I think that was the where do I have that? So that I think was the first homework that we had. So one was yeah, that is boring. Homework 2, that is less boring. So this is in principle quite trivial, so let's just copy the instruction. Create a new project. Create a project. Console, next HW1. Okay, we don't need that. Let's paste our instructions. So first thing, we wanted to split a 64-bit variable. So data is equals no x. Let's fill it with something interesting. 1 2 3 4 5 6 7 8 9 0 A B C D E F. That should be enough. That should be 64-bit of data. Yep. And we want a oolong, so we can copy those things. Actually, you can take the name from here. Zack. Well, as said, this is quite a simple. So out high 32. High 32 is this. Let's also make some low ups. Out is fine. Low 32. Low 32 is just this and XFFFF. And again 4 more Fs. Yeah, high 16. That will be well, it depends from where we take it, but we can either normally the idea of high 16 would be to take the high 16 bits of the lower word, but we can also take it from the other, so this depends on what we prefer. So 32 oops, plus is it correct? That should be correct. 32 plus 16 and the other, but okay, we don't have those types defined, so unsend long, unsend short. What did I scroll up here? Yeah, okay, I said the other option would have been just to take, I mean, this will not be like equivalent, but what one would also usually intend when saying that he wants the high 16 bits of something, we could take them from something that's already 32-bit. But as I said, this is not the same thing, so it's this, if you want to so this one will be this one will be that part, this will be this, and this would be the high 4 bits of the lower word. That would be that. Okay, so high 8 bits, so let's see, char 64 minus 8 is, what is it, 50, 56, 64, 56, yes. That will be, okay, I need to add null x to all of them to be correct. Yeah, and if we would, and of course here low 8 is just, I can copy this, just the last two ones. Let's remove this to be in sync with the home example. Yep. Let's just run it and see if it really does what it should do. So I just need to enable hex view. Yep. 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 Perfect. It's working. So that's first part of homework 1. Second part of homework 2 that I don't remember by heart. Let's get our helpful cheat sheet. Okay, so we have 1 in the sign, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 for the exponent, and the rest is just the rest. So we have float in, let's call it, I don't know, 1 to 3.456. Then we want these 3 things as result. Okay, so sign is the highest bit. So first of all, what we can do is we can unsign int data is equal. So first of all, we will need to somehow get access to the raw byte. So asterisk reference this and what was that reference Sternchen. Yeah. So what we do here is we are taking a pointer on our float, we are casting it to a pointer on an int, and then we are just reading the data as if it would be an int into our helper variable. Now we want the highest bit from there, so we go in this direction, 31 and null x1. Oops, just to ensure that we don't. I mean, this is not really needed because we know there can only be one bit left, but it's nice practice to ensure that you write the code in a way that even if you would change the, for example, data here to an int64, that the code would not start behaving completely radical. So okay, the next one is the exponent. Data, we shift it here by what do we need to shift it by? 31 30 23, I think. 23 plus 7 is 30. Yeah, that seems right. And null x ff, and then the rest of the data is just data without a shift, and so we will need binary. That should be 21. We want 23. That should be 23 ones. That sounds reasonably reasonable. Yeah, that is fine. Zack. Okay, let's feed this into our reference thingy. What was it? You entered 0. Okay, this of course does not. No, yes, it tells us the exact numbers. Perfect. 0, 133, and 7793017. So let's see if this will work. Okay, that. Let's recompile it again. Okay, so this is 0. This is. We need to disable hexv again. Okay, that needs to be unsigned in that case. Output. Yeah. So this needs to be unsigned. But the value is right and the mantissa is also right. So this is the way of doing it with well, binary operators, the quickest one. But one thing that you learn later, unions is also a method to get the same data. So let's do that. Oops, union. Let's put this float, and then we need the type. Then we take our unsigned int, sign double point 1, comma, maybe we should make it like this. Yeah, that looks nicer than exponent 8, comma, and mantissa was 23, and that adds to 32. Yes, it does. So we have all the bytes. So again, we assign new float as equals this thing. We should give that a name. Fu float, and we have f sign mantissa and mantissa. Then how should I don't know, print that maybe. Let's print it out. F sorry. Sign, and we say sign Prozent-D Strichpunkt, sign Doppelpunkt Prozent-D Strichpunkt and Prozent-D Strichpunkt und Prozent-D Doppelpunkt fehlt und hier auch. Und let's add a Strichpunkt just to be nice. This doesn't really matter, it's just what will be printed on the screen. So let's run it. One, wait, 88 is wrong. Why did that fail? And 1 is also wrong. That I think I made that. I think the order is wrong. Might be that needs the wrong order, because other than that, that should have been working. But I think that it's really possible that the byte order with this representation is inverted. Yes, now it's fine. 0, 133 and 7793017. Yes, so that was the first homework, and the desired solution as well as an alternative solution which one can use if one already has some more advanced knowledge. So if you did this, this is also fine. Good, any questions, or can we proceed to the next homework? Okay. If there are no questions, then let's open the next one. Yes, it was this unholy loop example which was so confusing. So if I remember correctly, what was the right solution to that? In principle, it's trivial. We have this loop that we have as a demo, and then we have a normal loop. And what we want is just to make, before I run it, I should disable all the useless stuff so that we have nice machine code. Properties. Let's see. Nope. Code generation. Nope and linker. Nope. Yep, passed. Okay, so if we step through the simple loop, we see that the order of operations is first assign. So far so good. Then we have a jump, which we do immediately. So we have if we want to change this, so then we want to jump, go to let's call it x66 because we don't yet know what it will be doing. Or rather, go to we know what it will be doing. It will be the test. Go to CMP. Wait, one moment. So yeah, go to CMP. CMP is here. Doppelpunkt. Okay, then we do our comparison here, and if we are done, we go to done. Else we do our printf, and then we make a jump. So we don't have anything here. We just have a go to next. I mean, the names are arbitrary, of course. Next is here, and we paste the code here. Oh, sorry, we already had a next, and it cannot be called next. No, it can. We just move the label down. That's fine. We don't need go to next. It's just the increment code that we have here. Yeah. Yep, that should be working. Let's run it. So what's the task? It should print like 10 times just the content of it, and then be done. Yeah, 0 till 9, and the other one does the same. So that was everything that was homework 2. Just add the jump here and move the next to the right position, move the thing to the top. So the idea is that everything that this part pretty much is just this whole part, and at the end you only have a label and one goto, so that you don't spread the code that makes up your loop semantics across multiple areas in your code. Any questions about that? I know this was kind of confusing. because it was not really clear what is to do. So I think I said the last time we talked about it that I will not create this exercise since it was a bit too misleading. But if you have any questions, that would be the time to ask them. No questions? Shall we proceed to the next one? Okay, I guess we shall. So that was the next homework. But maybe I should add the dates so that it can be found quicker. I think that makes sense. This was here. And that was the first one. Zack. So 1, 2, and 3. So what do we want here? We have a... Wait, that was the wrong position. I screwed something up now. That should have been here. And this should have been there. Yes, now it's right. Okay, so we have a union, we have a lot of things in the union, and the task is that is just a, how you say it in German, Fleißaufgabe, a task to show that you are willing to do everything that needs to be done, even if it's completely unnecessary. Okay, so we have our team. So how do we start it? Okay, let's just go with the most simple thing. So size cannot be changed. Flags we also need to set. Okay, so here we want byte 1. So test, let's just call it underscore. Should I call it test2? No, let's call it maybe B. B for bitwise. Okay, we want byte 1. That is this one, and since we saw that they are reverted, so that will be the wait a second, so this is not MSB, this is the LSB, MSB. Is that correct? Yep. So we want byte 1, that's the least significant bit. Okay, this is easy. We just go with, let's maybe define another variable for this, just var f, what was our initial value, unsend flag int, yeah, with the same thing. Okay, so var f and null x ff. So we can test whether it will work, but it should. So this the value should be, okay, let's make hex view AA, and we got AA, perfect. Now we are assigning AA, well, why not, to the second byte. So the second byte is here. So we want to do the same for our var f. Yeah, that starts getting complicated. So first of all, we need to clear that byte. So this is, let's do it without shortcut. So this thing and the inverse of null x ff shifted by 8. So this clears all the bits in the second byte, and then we assign the bits to that byte. Okay, let's see if that works. So okay, so we have ABAA, and after we do it, it should be AAAA. Yep. That worked. Gut war 1. Why did we do it twice? Okay, that's kind of the same thing. Boring. But why not? Okay, now we want to get the nibble. So the getters are always much more simple because we just take what we need and we don't need to first clear anything. Nibble 5. Where's nibble 5? Okay, nibble 5 is here. That is good enough. So that was that. We want a nibble. So first of all, we need to shift that by 16, since this nibble is located in the third byte, and we want x ff. Ensure that we only get what we are interested in, and let's do nibble 6 as well. So that's 20. The rest doesn't change. Let's make a breakpoint and see if that works. So test 2. I'm sorry. Sorry, that was a business call from my colleagues. They were searching for some parts and could not find them. Okay, so we wanted to test this. So we should have just the letter F, and we get the letter F that works, and 3 is 0, and this is, wait, that is not good. Wait, nibble 5, nibble 6, why does this not work? 3 is 0, nibble 6 is 0, and B. Just to clarify, is this still the same thing? Yeah, the content is the same. F and 0, so 0 is the right value. Something's wrong. So let's first try the 16. Yeah, F01, and then the 20. Oh, sorry. Major snafu. That's not a nibble, that's a nibble. And this should not be 16, but no, that was fine. Just the mapping was wrong. Yeah, that would be then 0. So let's run it again. Yeah, 0 0. Right, no, sorry, the one was 0f, yep, 0 0 0 0, perfect. Okie dokie, next one. Oh, so many assignment operators. Na gut. So var f is gleich var f. We want just to clear one bit, okay. And tilde 1 shifted by 29. So we clear the bit. Sorry, no. I was working already on the next line. So this is this. If it's one bit, we don't need clearing thingies, so it's easy to set the bit. Yeah, but sorry, this one needs some more effort. Yeah, so let's say das and nibble 7. Which one is it? Nibble 7 is here, so that's like 8 and 8. This is 16, and another 8 is 24. So that starts at 24. That is good. That helps us. Var f and nibble ist 0xf. Das Inverse davon geschiftet, also das Inverse geschiftet by 24. well, and we add a new value, also shifted by 24. That should be right. So let's add a breakpoint and see what happens. So we want the result to look like this, and currently we have that. If we now execute our operation, it works. Yes, perfect. Now the 2 bit sets, they will definitely work. Let's just skip over them. Oh, shit. And see that the results are the same. So this thingy is now 2A0FAA, and the other one, oops, I think, oh yes, that was a bit too fast. Now it's fine. Yeah, and the other one, nope, that is not correct. So what is wrong here? Let's test it step by step. So we put a breakpoint here. This is the desired outcome. The input is, and was it already set to 0? Probably. If we make a step, then it's still correct. We were just apparently clearing a bit which was 0 anyway, so this works fine. Now we add one bit somewhere else. Let's try this one. So this is the new value, and now if we do that step, this should but it does not. This shifted to the very back. Oh, sorry, that's the problem. Oops, I was a bit distracted and did not do the right thing. Obviously a smaller operator doesn't make sense in that situation. Okay, this is U and this is our goal. Still not quite right. 1 bit shifted 30, bit 30. Wait, no, we start with no. Is that really bit 30? 30, 31, 32, seems so. No, it's not, because we are counting them from starting from 0. So this is 0 to 8. That 0 to 7. That is 8 to 16. That 0 to 7. That is 8 to 15. That is 16 to 19. That is 20 to 23. That is 24 to 20 what? 9. No, that cannot be. Let's write it down. 0 to 7, 8 till 15, 16 till 17, 18, 19 till 19, 20 till 23. I think I missed one of them. That is then 24 till 27. I think we're missing something. We are missing a couple bits somewhere. Because 7 we have then 8, 9. No, that should be fine. 28, 29, 30, and 31. That's the offsets. So if we need to go here each time one less than what absolute bit number the bit would have. Now it should be fine. So as you see, unions are quite useful to not to easier manage such bit fields, because then you really can avoid screwing things up. Yep, now we get the same output. So let's continue to the next one. We want to set the same bit to 1 again. This is boring. Okay, we don't need to do that, we already did that. Okay, here we just have 2 more getters, that's easy. P is equals well, first let's shift that 31 and then and 1 and 1, and the other one is 2. Wait, sorry. Yeah, now it's right. Okay, let's run and compare the results. So this is 0, that's 0 as well. This is, are they both 0? Yeah, they're both 0. Yeah, but it's still working. So this was homework number 3. 1, 2, 3. Homework number 4. Okay, so any questions at this point?
Yes.
Okay.
Theory of bits you have done in helping here line 100.1.
Yeah.
Yes. So can you maybe repeat what's happening here exactly? So
Okay, so let's, how do we do that? So let's start with what is inside this thing. In this point will be this. So we start with this value, right? Then first operation we do will be generate a temporary variable in temp is equals this. And this basically is then null x ff 0 0, so it just shifted by 8. Then we invert it, so this, oops, this is equals this. So now we have, what do we have? ff, no, 0 0 ff, because like this fills it up with, sorry, with zeros, and we just invert it completely, so we get this. Then we make this is equals this and that. So this is an AND operation, and we end up with only those bits set which are set in both, so this one gets cleared. And then finally is equals or we should make a second temp variable. So this thing is x null a null. This and temp, so the result is then here AA, and we are done. Okay, any more questions? Okay, if not, then let's proceed to the more advanced homeworks, namely to the simple list thingy. Did you open it recently? Does not look like it. Project. No, sorry. I clicked on the wrong tab here. File. Open project solution. Simple. Was just called list? Or maybe I saved it somewhere else. Probably on the tail one. Simplest. Yeah, why not? Okay, so one is implement the remove from list. So we have our list somewhere here, and we want where was it? Maybe we should just print the list, then the remove, and then print it again. That makes sense. I want to remove which data? Let's say I want to remove data y, because why not? And what was data y anyways? Y was 5. Let's run it quickly to see what we have in our list anyways. Because if this is the last one to be removed, wasn't there none of? No, there is one. 5 is 5, but we actually don't print that variable. So let's go with that. We want to remove this one. That one we should be able to find here. I guess x is I don't remember the structure. Let's see. Dump. So we want variable x, and variable x is the nope. Then let's see what this function does. Okay, it checks variable 1. So we'll be removing whatever variable 1 has, wherever variable 1 has. And variable 1 has a 3 in the third column. So we expect this column to go after our remove from list did its job. So let's go to remove from list. We already have the data. We need something to step through that. We can, I guess, start with just repurposing this thingy. So we start with the head. We iterate through everything. We have here the data. Just check if data is this. Oops, if data is equals mdata, then we want to remove it. And in principle you could also break, because we don't assume there being more than one copy of that data. Jawohl. What did the homework said exactly? Implement remove from function. Okay, it doesn't say what to do else, but I guess we will not delete the data since we can delete it later on, since we have the pointer to it anyways. We just need to unlink it from the list. So current data, sorry, current okay, we need to somehow have the previous one. Because we start with the head. We have the current, and this is just, so this would need to be a, in principle, a reference such that we can modify current. So in principle just current will be equals current next. That could be as simple as that, because we have here as reference, so we can change current. We check whether current data is what we want it to be. If it is, then the current element will be removed. We need to delete current as such. Where did we create it? Did we use new? Did we use malloc? We use malloc, so we need to free that. So we need a copy of that. Per old. Now we did this, and then we not quite right. We need to assign it, and then we can free or that should be it. Let's run and see if it works. No, not good. We need to do it with a double pointer. This will otherwise not work. So we need this. We need that. Actually, that's already what we want. Current asterisk current, and this should be reference. What am I missing? Ah yes, I changed the name. Let's just stick with pcurrent. Yeah, right. Great. Okay, so here we need to change that, here we need to change that, here we need to change that, and that will, yeah, well, now it should work. So it printed the list once and then printed it again without the third line. So maybe we should add here some text. For and after delete. Suck. We don't need the breakpoint anymore. Yeah, well. Okay, now let's test the edge cases. So when the value is 1, so the first one and the last one. So here let's say 1. So I want to delete an entry from the head. Suck. Yep. And then the other option when the value is 4, which would be the last entry. And if like head, tail and middle works, then everything works. Yep. So this is working. Part 2 implement a double linked list bidirectional list. Okay. Yep. Sorry. Okay, where were we? Ah, yes, the double linked list. So where were we? Yes, so we need to enable this. Add list to top. Data. So we have our head. So we add always to top. So p head is still p head. Oops. Previous will be equals new, and in new previous is null because there is nothing on the head, and then we shift this down by 1. Seems reasonable enough. Add to bottom. Okay, that's the other way around. So first of all we need to find the bottom of the list, although we could have a much simpler add to bottom, since we could have 2 pointers, one pointing to the head and one pointing to the tail, but since we are here, let's stick with that. Right here, so preview is equals that is not good because we lose track of what we had. Because now current is just already a pointer on the next in the last entry, so this is not good. Okay, because this was like a quick way to do it, we can comment this out And here go the longer way, but this is also not that much better. We do that the smart way. It really does not help us either. Well, we start at that. Basically, we just need to introduce a temporary value which will hold the previous value, and that's it. Per previous is equals null. Because like if that would be an empty entry, then previous would be null. So we have to handle this case. So now we are inside our loop, and then the increment operation, that would be this thing. We want previous to be the current when the current is moved to the next, and previous to remain null if the list was empty and we never entered. That's it. That solves that. Right here, so we need add top, remove from list, find in list. Well, actually, find in list and remove from list don't need changes because they can just go from one end, so they are fine. Let's just put a breakpoint here. Let's make a breakpoint after each operation, and then see if what's inside the list is what we want to be inside the list. So okay, now head is undefined because there is nothing. If we make a step, now head has data and it doesn't have anything else. Wait, we have add to list. Don't we use the other one? Add to list bottom. We should use add to list bottom somewhere, otherwise this is boring. We were switching from one to the other. Let's comment both of them out and just make to add top and to add bottom. Yeah, that sounds reasonable enough. So let's see. Zack. Genau. So this was still 0. Then we make a step. Okay, that already did not work as expected. Why? Head. Add list top. Head. Now let's step through that. So again, Zack. Genau. Also we allocate a new one. That is not good. We cannot dereference this. So we need to have here a check. So if this is defined, then use it, else assign null. Okay. Okay, now step. Wait, we have not changed. Before that it was working. What did I change? I mean, I didn't change here, I think, much except for this and that. No, I did. Yes, that's the problem. In principle, so basically what we should do is just make an if here. So if there is a head, then we can do that. And if there is none, so if this is the first thing we are entering, then preview will be pointing. So no, this will not be there. This will be pointing to null. Yeah, now it should work. Step. Sorry, almost right. Yep. Okay, finally. So our head points to something that has previous and next set to null, as expected, since we don't have anything else in the list. And we have the data set. Then let's make a step here and see. So next is pointing to something, where next points to nothing and previous points to next. So basically, if we just switch between next and previous all the time, we will be basically just going from one object to the next and the next, and so like jumping between those two. So this works as expected. Perfect. Next step. We wanted to add something to the bottom of the list, so let's see. So we have next, which has a next, which has an wait. So head has one data, next and next, and the next has nothing. And here, the one added to the bottom of the list has a previous, which points to the previous. Yep, that seems to be working as well. And last one, then it adds us another next entry, which then points back to the previous one. Should be right. Let's first of all print it again, and then print reverse, print list. Which is not so ideal because we don't have that tail, but okay, we can do that anyways. Let's print reverse. So ideally, with such a doubly linked list, we should have two values, a pointer to the head and a pointer to the tail, such that if we want to do something from the back, we don't need to first find the last entry. But since we did not hit this pass, ja, das muss eigentlich tail sein. Here we will do a find tail. Aber erstmal das, so per tail ungleich 0, per tail per previous. Okay, we need a find tail function, pp head. And we had some already a find tail function, at least something like it, in this add to bottom. In this, yes. But I changed it slightly. So we have here, and preview will be the last valid entry. Yes, this basically will be the tail. So we will keep it as pp tail. We should initialize it with 0 with null to be sure that we will return something that is valid. Okay, so let's run it. Oh yes, I should call it find tail. That of course helps. We don't care for those breakpoints. We just want to go up to here, and we have print forward, so 2 1 3 4, and okay, something is broken badly. We will need to fix that. So first we will just check whether add to top works fine. No, it doesn't. Well, we're missing the last entry, so maybe our find tail function is wrong, because here Then we go to the next. Pim pim pim. And if this one is not, why this is not null? So if this one would be null, then we abort. Yeah, but if this one is null, then we abort. That sounds reasonable because we cannot do anything with that. Let's first validate to be sure that it really is just a problem with the very last entry. Here 5, 5, 5, 5, 6, 6, 6, 6. Now we expect just the 6 to be missing from the dump. Nope, it is worse than that. It's somehow thoroughly broken. Then we need to fix the add to list top. Wait, or our find bottom is wrong because we have 1, 1, 3. No, that seems really completely wrong. But also those here are not quite right. Wait, 1 second. So, okay, okay, that was a copy paste mistake, but that will not help with there being values missing. You have to have 1, 2, 3, 5, 6, and then we have 1. Okay, that's so add. Apparently something's wrong with our add to list stop. Let's think again. So previous, because we add always to the top. So if we already have a head, then next is the head of the head's previous point to us, and we become the new head. That sounds right. Why isn't it? Let's run it for the second case step by step. So we step in, we make the new element, we assign the data, we already have a head, so the new element next. Wait, we call it add to list top. I think this is. How did that look originally? 1 second, please. I think I broke something unintentionally. Simple list. 1 second. So where was it? That's not the right one. Simple as 1 second. So next and so this was wrong. That should have been. But why was that crashing then? Strange. That should be right, and then yeah, because the next one is the p head previous of the old head is that should have been right the way it was very in the beginning, but that was crashing. Why was that crashing then? Let's run it again. P head so this, so if this is not null, then we can assign it. And other than that, there should be no now it should be right. Let's quickly check what this will do. Well, it doesn't work quite as expected. So again, breakpoint. So we go in. We make the new one. So then the new element, the next in the new element will be the old head. The old head is not null. The previous one is the new one. This is correct. And the previous one of new, because new is the new head, or rather will be soon, is null. This is correct as well. So let's see head. Next is we have not yet made the head. Okay, now so head. Next is the next one, and it should reference the previous one. That seems right. So let's go to the next invocation of our function. So head point. So head contains number 3. Next contains and no previous, and the next contains a pointer to 1 and to number 3. That looks correct. Why doesn't it print correct? Presumably because our find tail function is not operating the way it should, maybe. Let's see that. So we start, and we have here a depth of 1, 2, 3, 4, 5 elements. 6 elements, wait, really? So we have 6, 5, 4, 3, 2, 1. Okay, that's fine. So we make a step, go into 1, 2, 3, 4. So this should be the tail one. It should have no more next. No, it has one next. Okay, so that will be the last one. Yeah, next is non-existing, so this is the tail. And now we break out of it. So we have the tail. If we now go through the previous one, so we start with what was it, 1, then previous should be 2, previous should be 3, 4, 5, and 6. Okay, so this function works, and we correctly construct our thing. So what's the reason this print thingy does not work? It should be working because we start with tail, we go with the previous route up. Let's just run it again, but there must be something wrong apparently, since it did not. Yeah, it did not work as it should. Find the tail. Okay, we already have defined the tail variable. But let's make here find tail, and then that is somehow wrong. That's 2 asterisks, and this one, that one would in principle need this to be dereferenced, and tail would need to reference, but this is fine. Let's just step through it step by step. First check whether the tail is really correct, but it's likely that it is. We already checked that preview, 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 preview. So where were we? Tails, that's, yeah, that looked okay, so let's go in it. And it's not null. We print the first line. Yep, then we take the preview of that. Oh, and we already out. That is not good. Sorry, I stepped over it. I should have stepped into it. Step into. So now, shit. Again, a copy and paste bug. When I created this function, this of course also needs to use the reverse one. And yep, so that is fine. Now let's try replacing some of them with add to bottom. Maybe the 3 in the middle. Okay, let's run this. And so 6 to 1 3 4 5 6 to 1 3 4 5. Yep, that seems correct. So that much to the simple list. And what else did we have homework wise? We had the hash table, and then we had also one more, the IO buffer. So I don't know what did we say the last time. Do we want to take a look on the hash table today as well, or during the next lecture? Okay, perfect. So what we can do at this opportunity is we can port the simple list from C, because now it's basically just done the C way, into a C++ implementation, which I think might be interesting to do. So let's create a new project. Yeah. That is a good point, and we only have 1 hour left. But I guess we can do both. But let's maybe first then start with containers. Although it would fit to do the list. Well, the containers are quick. Let's start with containers. std containers. Teil 1 create. Okay, so basically what you will need is since we want access by offset, that will be a vector and a map. And let's first start with the vector, so std vector, small, and then we can specify what thing we want to put into it. We can really put anything into this template. We can put an integer, and fact. We could also put the whole class, like a std string, small s. So these templates really take anything you can throw at them, and they are quite nice in use. So first of all, you have the pushback command, which allows you to add something to the end. So let's say pushback 1, 2, 3, 4. You can also, I think, okay, with vector you cannot push front. With other types, like a list, you could do push front, but the list has but the list has the downside that you cannot that you cannot access elements just by offset. Push front 1, 2, push back 3, 4. So with the vector you can write int test 1, and then just square brackets and then let's say second index, and if you run it you will get the value at the second index. So in this case well, at the index number 2, in this case it's the third slot, since it always starts at 0, and we get the value 3. And I think I should be able to print the content. Yep. So you can even print the content in the Illuminate window, and you can use those also to change the value. So this is by reference, so we can change to 1, 2, 3. Let's change it to 9. So if we print it now, oops, you see we changed the value from a 3 to a 9. So it really behaves like a normal C++ array, just that if we try to access something that's completely invalid, like 25, it should throw some sort of exception that tells us that this was not good. Oh, or it crashes, that's also possible. In this case apparently it crashed without posting an exception. Interesting. I mean, it will crash at some point because it's probably doing something, although it may really also be caught in an endless loop. We can pause it and see. It's just completely dead. Yeah, that is not so great, but we can try to find out where it got stuck. I mean, it makes a sound. I think it tries to show an error window, but it fails because this thing here is a different a console application. We can switch it to GUI application. That might work better. But also main. I think WinMain needs some prototype. No, it's just crashing the same way. It does not. Usually this should be caught by the debugger. I'm not sure why it in our case is not crashing the way we want it to. I mean, we can try even larger number. No, it just make a sound. Do we have something in the output maybe? Nope. Interesting. That this should be a bit more helpful. I mean, it's a debug build. std. Let's try to debugging will also not help us. Well, it's not good that it crashes without a warning. Can we somehow provoke it to? Nope, we cannot. Oh, now it worked. I don't know why this did not work earlier. Okay, well, now it's working fine. Yeah, and it tells you even where. So it tells you, unfortunately, just a line inside the definition of vector. But if you go on wiederholen, on repeat, then it should, yeah, break where this assertion occurred, and then you can check in your call stack from where you came, and then you see, here apparently I had the wrong offset. So of course a C array would just silently corrupt memory while the vector here tells you that something is not correct, and then you have the opportunity to fix it. And a set with list, you cannot do that. It's just a linked list, it does not have positions. And what you can of course do with those types is you can so with the vector, it's if you think about how to iterate through the values, you can just use a counter from 0 to size, but you might be wondering how to do that with the list. And you can do that, so maybe as an example, let's write it down here from is kleiner invect size e++. So that's how you just go through everything in a vector. But in a list, of course, this will not work. Sorry, we should also write down. We should also use this so that you see how to access the value. But as said, in a list, this does not work. So what you need to do is you need to use such so-called iterators. There are, in principle, two ways how you can define those. So that's the long way, and you could instead of this just, and of course you need a name. But of course, instead of writing this, you could just write auto, and then the compiler would pick it for you, because the iterator you need to first assign it, and that's where the compiler would then get the type information. Just go and begin, and then you iterate as long as e is not end. And then you can use e++ or ++I, it doesn't really matter, to increment the iterator to the next object. And now if you want to get the next object, you can just dereference the iterator, and this will give you the value. You could also use this to assign it to the map, I think, at this point. And of course this works as also with vectors. So this going through a container using iterators works always for all the different types. There are just slightly variations. So here, of course, it needs to be a vector type. Yeah, other than that, it works fine. What you can do? There are quite a few functions which you can use with iterators. So, for example, you could for example insert something at a position pointed to by an iterator. So if you would, so we can find maybe something first. Do we have a find function for that? No, not in the standard library. So if you would write yourself a find function that finds you something in the list and returns you an iterator, then you could insert something then at this position of your list using insert, or you could remove it. So for example, inside the loop you could look and remove all the values which are, yeah, we could do that as an example. That's actually a nice thing, but this needs some adaptation. So let's leave this as an example, and now remove all even entries. Now the most important thing to know when removing things inside the loop is that the delete operation will invalidate the iterator, but we will come to that in a second. So if this modulo 2 is 0, yep, that means it's a multiple of 2, then we want to delete it, and else we want to go to the next one. And since removing an element from a list invalidates the iterator, the remove function in the list is implemented such that it returns you an iterator to the next element in the list, or to end if, wait, that's not right, if there is none. So whenever you are removing thingies, that should be right. Why is it complaining about int list remove iterator? Was it erase? Sorry, it was erase. Oh, that's nice. So if they have a remove, then they actually have already a function that allows you to remove by value. I know they have a find function, just called differently. It's index of, I think. No. If they have a remove, they must also have some sort of find. Begin array, empty get allocate, insert, max size, merge, pushback, remove, remove reverse and reverse size sort, splice, swap, unique. Yeah, it depends on which exact version of the framework you have. I think some of them should have a find function, especially that if they offer you a remove function. But anyhow, sorry, as I said, the right one is erase. And what you can also do is, if you want to go through the list backwards, you can do this as well. With an iterate, you just need to use rbegin and rend. But I think this is then called somehow reverse iterator, yeah. Oh, and then you just go in the other direction through the list. So even if, first of all, you see the list is internally a doubly linked list, like the simple list after our change, and that's it. There is nothing more to say about that. You can remove by using this erase. This would work with a reverse iterator as well, so it should be defined for both versions. Wait, but I don't think rbegin and rn. Yeah, that should be fine. Okay, so this much to the list, and let's see the last type that will be really useful. It's map, and this is internally it's a sorted binary tree, and you can specify a key. So let's take an integer as a key and a string as a value. Double punct string, and we call it string map. And you can first of all access the different keys. So this one method, you can access values 2, 3, 4, 1. And you can also use the insert command. So if you do it like this, you don't know if there was something before in the list. You just know that now in the map, and you know that now for the key 1 you have this string inside it, and you can of course just get the values from it the same way. But first let's finish with the insert. And this is a little bit convoluted because they don't, at least I don't think that in the standard set of available commands you have the ability to insert something just like with, for example, Qt, where you just write 1 comma and then the one is string. Now you really need to to make a pair object of type pair int comma string std, and then initialize it with 5. Yeah, and what you get as a result, let's go with auto because I'm too lazy to type down the type, is a pair again, which has one parameter. Which was it first? One of them is one of them is a boolean and the other one is the iterator. Okay, then it will be the second one. And the other one is let's go with auto again. The iterator where it was inserted. So I mean, we could write down the iterator by hand if we want. So it is this dot. So if you insert an object like this, then you get a value back that tells you whether an object for this key already existed, or whether you have and you have overwritten it, or whether a new entry was created and the key was added. And then, as said, you get the iterator so that you know where you inserted it, because this insertion will be somewhere in the tree, and you might want to just know where it was if you would want to go from there and do something. Now, the next interesting thing about map is that since obviously you have an access by a key, and the keys don't need to be sequential, they can be random, pretty much. You also have a find function from our map, and there you just say which values you want this number 3, and what it returns you is just an iterator. A found iterator, so it returns you the iterator to where this thing is in the map if it finds it, and if it does not, then it returns you what is it, map punct end iterator to end. So this is, so you need, of course, whenever you make make find, you need to check whether the iterator was found or whether you got an empty one, because this value did not exist there. And as said, you can also iterate through a map. So let's be lazy and let's not be lazy. Let's take the whole iterator here. As said, normally nowadays you would rather just use the auto keyword for those types. So this part works the same, but getting a value, well, it kind of goes like it. What was it? The string view, the string is value. So you can access the value. Can you? Maybe you can't. You definitely can access it by sorry, it's a pair. In Qt it's different. The other framework allows you to dereference a iterator for a map. I think STD does not. So first is the key, so int key, and then string value is e second. Did they really not implement? This is basically an iterator. I find it intriguing that they have not. We cannot go there. That they have not allowed us to get the value by this asterisk operator. But apparently they did not. Okay, so we have here the asterisk plus minus. This one we have as well. Okay. I know why. It will have it, but it is but what you get once you do it is you get this pair which then has just these two values. Well, anyhow, this is how you iterate through a map. What could be as interesting? Yes. So if you have if you found something in the map, you can use in principle the iterator to erase it. So for example here, if we found 3 and it is not sorry, that would be not found. Sorry, that would be not found. If it's not null, then we actually found it. And what we can do is we can erase it. So you can, using find and erase, select which keys you want to delete from a list, from a map of values that you have created. One thing I want to think, I think vector should not have erase. On vector you can also make arrays, but this will be quite inefficient because vector, in contrary to list, keeps all the data internally in one memory block. So if you make arrays on the vector, then it will remove the element and we'll need to copy all the other elements by one. So we can also then make an insert, I guess, but that will again be quite inefficient. With the list, however, it will be very quick to insert and erase elements because it just needs to change the linkage. It doesn't need to move any larger amounts of data in memory. Yeah. Any questions at this point about these container types? Mm-hmm. Yes. Any more questions? Okay. If there are none, there's one more interesting type called unsorted map, which in principle is a hash map, like a hash table, like we have implemented earlier already. We can try this as well. But in practice, it behaves the same way as normal map with regard to what you can do and what operations you can do. There are just some minor differences. So, for example, this find function here, it really looks for this key and this key alone. There is, however, a second function. Actually, there are two, upper bound and lower bound, which allow you to search for, what was it? For a value that is the key or one or larger. So it allows you to find the position inside the map, even if you don't have the exact key. Upper bound. I just never remember which one did what. So let's say we want to find. Let's say we have erased number 3, but we still want to find 3. We can do that. And the main difference is that one of them will always give you like the exact key, or either one higher or one lower, while the other one will just give you the next value to a key that you already had. I just need to check which one is what. Okay, so upper bound this, and lower bound then will be the one that gives you either the right one or the one next to it. Yeah. C does not have any classes, so it's just a C++ thing. Okay, so we can first of all not erase 3 and see what iterators we will get. In C and C++, while it's technically two languages, it really just one is an extension of the other, and nowadays doing everything in C++ is just fine. Okay, so the upper bound, as the description goes, gives us the next element after 3, whether 3 exists or not, and lower bound gives us 3 if we have 3, but if we remove 3, then both will just give us 4. Which apparently there was a reason why people wanted this differentiation. So the first one gives us 4, and the next one now gives us 4, since we didn't have the 3. And of course, if there would be nothing that comes after 3 in the map at all, then we would get the end iterator, like we test for it here, to denote that there is nothing more in the map. And those functions, of course, are not present on the hash table. At least they shouldn't be. How can that be that they are? Because the unsorted map should be a hash table internally, then it should not be able to have those functions. Unsorted map. Unsorted map. Well, in the manual they are not listed. I'm curious what it will do if we try to run them on the unsorted map. but they seem to be defined. Okay. No, they're not. They somehow are using a similar template such that you can, such that the IntelliSense tells you that you could use those, but in fact you cannot use those. Yeah. Good. So, any more questions? Yeah, maybe if you are wondering where you can find all those classes or map and stuff, here you can find a manual for map and for other container types, together with all the functions that you have at your disposal. So there are quite a few more, but the most important ones, as said, are just vector, list, and map, and of course unsorted map if you need that for performance reasons. So, any questions?
You say said for performance reasons, so the cache application is faster than the other one?
So it depends, as said, on what you are doing, because in the hash table, ideally the speed with which you can retrieve an element is constant, so it doesn't matter how large. If you have 10 elements, million elements, 10 million elements, the speed of retrieving one element will always be the same. While with a map, while it's still a very favorable amount of operations required, you have a performance of order logarithm of the amount of elements that you have inside. So if you double your map by a factor of 2, then you need one more operation, on average of course, to find what you were looking for. If you double it again, then again just one more operation. So it scales very favorably, but still of course the bigger the map gets, the more operations you will need at some point. While the hash table will always have a almost instant lookup, since it's just a constant amount of operations, no matter how much entries are in there. Of course, this is the ideal case. If your hash function is really bad, then that will not be the case. But this template library has hashing functions for the generic types which work quite well, so normally that should not be a problem. Any more questions? Okay, seems not. Yeah. So if there are no more questions, then we could try very quickly to port our simple list to C++. I think that would be nice to do. Create new project, console project.
Maybe just one question. Why would I use the map instead of the hash table? So I don't get what's
The map is ordered. So if you have like here 1, 2, 3, 4 and you iterate through your map, you will get the values according to the greater or greater equal operator for your key. So for example, you could abuse a map to sort strings. You can throw in strings into your map and then iterate through it, and then the result of the iteration will be the strings as sorted by which one is greater than the other one, basically. And of course for strings that's maybe a bit a useless use case, but for any other thing where you have numbers or something, this can be used for sorting this way. And you can create other data structures which need this this order property. So for example, what I did a long time ago was I implemented a class that allows you to represent a file from the first byte to the last byte, and then set for different ranges within this file, different flags. So for example, you could first you would set that the whole range is empty. As you start writing data to the file, you would say this area contains data, that area contains data. And the idea how this worked was that you use as a key the starting offset, so the offset in a file, and then you keep as a value well, different flags plus the length of your current element. And if you would not have this order property of the map, you could not implement such a structure efficiently, because here you can really have like 100 states within the file for different portions of the file, and then if you just query a given offset, you will get a result very efficiently. With a hash table, this wouldn't work because the different values would be just somewhere within the hash table, and you would not have this upper or lower bound functions at your disposal. So the idea is that you can query an offset for which there is no key, because it's just within a range that has all the same flag sets. So of course, if you have a file, you don't want to make like a byte array and then set like really for every byte in the file a state, because then your whole state structure would be a couple times bigger than the file you try to describe. So if you would want to describe a file that can have many gigabytes in size, that would be impractical. But if you make a system where you really just save like ranges, basically, so like from range 1 to 10 it's this state, from 10 to 100 million it's another state, from 100 million to a gigabyte is yet another state, then you have just a couple entries. But then you want to retrieve the state information for any offset within the file, for example. So then you just say I want the offset for 100 million 21 for the 100 millionth 21st byte, and then you get using I don't remember whether I used upper bound or lower bound, but using those functions you will just get the next closest entry to it, and from this entry you can then see, okay, the entry of course it should be long enough to contain this byte, because otherwise you should have ended in another one. So you make a sanity check, and if this is fine, then you just take the value and then you're done with it. And I guess there are much more such things where you can exploit these properties of a map, that you have this order and the ability to get the next best result towards a given direction. So this function, it does not give you like the closest from both ends, but it always gives you the closest or bigger, like the right one or bigger, or the next bigger one in case of the upper bound function. So this way you can very efficiently operate even if you don't have the whole key space filled in. So that's just one example. Other reasons why people would want to use a map other than a hash table is if they don't know if they have a good hash function, they're worried that they may end up with this hash table degenerating to pretty much just a linked list. That can happen, and if you use a map, then you are just on the safe side. So that would be another use case. Then of course you might just don't care about the performance. If you just have a couple 10 of 20 entries, then it really doesn't matter. Another reason of course is that if you would have to implement those things by hand, well, if you would have to implement them by hand, then the hash table is much simpler to implement. So there is that. Yeah, but other than that, I guess, well, there is another important aspect. The map has a more or less known insertion performance. So if you are inserting elements, you know that it will always take more or less as much as a lookup takes, so log n, but it should never take longer. While with the hash table, if you run in a situation where you need to grow your hash table first, then the insertion will be for this one instance slower. So if you want to always have the same time, or at least always have a more predictable time, you could go with a map. But then the amount of work needed to grow the hash table is usually not so big, because they are just copying one large block on memory in one go. So there is an advantage to using a map, but probably it's negligible in this case. Other than that, yeah, I guess there are no more really big advantages to the map. It really just boils down whether you want this property that the data within it internally are sorted, or if you don't care for the order. That is probably on the practical side of things the criterion you would decide which one to use in the end.
Okay, thank you. I think
Mm-hmm.
that's explained it.
Okay, any more questions? No more questions? Okay, then we will try as quickly as we can port our simple list to C++. So this would be, so the entry would be okay, so we need a class that will contain, yeah, but this is actually quite boring. This really is boring and quite easy. Class as my list. Hello. Okay. Okay, so we need a constructor. We want it to be public. We need something protected. So as protected values, we want to keep the head and the tail. We should rename them to fall in line with our first defined nomenclature. And so this one, of course, we don't need the head anymore since we have it here. Okay, then at bottom is also quite we have not yet used the tail variable. We should use that then once we are done with the port. Okay, so here we need a reference on this, and let's just remove that. Okay, then remove from list, find in list. Those we need as well. So you see that the change is not really that difficult. We just replace a parameter which needs to be fed in externally with using some variables that we have defined on our object. Wait, is this? Right here, so print miles. Okay, we can move this as well. And find tail. We don't need. Yeah. Okay, then we have yeah, that is not so great. Since we are here recursively using this function, we will make a copy of it called implementation. Okay, this does not need that as well. Just then call it with reference to head, and this we can then move to be a private function, or let's keep it protected. And for the other one we need to do the same thing. Zack, zack, now of course it would be more elegant to keep to split that in a C and a H file, but here for reasons of being quick and don't caring much, we just don't do that. We need to name this here as well. And we said we want to actually use a tail variable, so here we won't have a find tail function anymore. We can here just feed in tail directly, but we will need to ensure that tail will work. So add to list top if head is not null. Yeah, but if head is null, then tail gets set to the same object. So if we only have one entry, then head and tail points to the same thing. And at bottom is kind of the opposite. So where do we have our head? What we try to do is we just try to find tail. So actually that could be much more simple. We don't need to search for anything. Let's just copy this. So we have data next. If next will be null because that's the last entry. Previous will be tail. Yeah, and if tail is not null, then tail next will point to us, and here of course the other way around. Wait, and this then will be tail. Okay, without testing it, that should be it. So in principle we could generalize this. No, we could not. Yeah, it's not super elegant because it's kind of duplicated code, but it cannot be simplified that easily even further without using some more advanced trickery. And of course what we would also do is at least put this thing here to be a internal data structure. Okay, that is not quite the greatest thing because now it's complaining we need to define it here. So that the compiler sees it. Okay, and now we can use it. So we just make an object of type mylist. List, zack. And then we just can bottom list print. So as you see, it's quite much more convenient to use it this way because you don't need to pass the variable explicitly. You can just use it like this. And of course, if you would have more than one variable which would be relevant for your like head and tail, then you would need always to pass both to the whole thing. Then here you save of course a lot of typing if you only need to paste one variable each time. Okay, let's run it and see if that works. If we did not screw up the add to bottom. That doesn't look right. Okay, something is screwed up. So first we just check whether at top works fine. But that one should probably that bottom has somewhere a copy and paste mistake. Okay, print reverse also doesn't work, but it starts with this with the 6. It just then terminates instantly, so there are both are wrong. Let's see. So we have a new object. We assign a new preview. Always assign to the top. Yeah, we forgot something. The old head preview, we did not assign this anywhere. This should be pointing to the previous element, so we forgot about that. Let's see if it now works fine. Nope. Right, we might not have it. If there was one, then it will be previous one, and now works. How much time do I have? 14 minutes. That is doable. So we already had a head element, then tail. Right, it only is true if tail is null. If we don't have a tail element, actually this we don't care if we have a head element. Tail, yeah, okay, try that. That was even worse. Sorry, that should be if we don't have a tail element. Yeah, now the one direction works correctly. So we had the problems here. Yeah, so basically we take this, paste it here, and then just swap tail for head and head for tail. And then the other direction should be working as well. Let's try it. 1, 2, 3. Nope. That we somehow ran. So let's see. We want to add it to the bottom. So we make a new element. We assign data. Next will be null. If tail is not null, so if there was already an element, then tail next shows on the new one, yes, and the new one preview, that should be null. Nope, that is not correct. Next should be null. No, that's why preview should be tail. This is correct. Then the head. If there is no head, then head is new, but there is a head. And if there is tail, then tail. And that should be next. Next is new, and now it should be fine. Yep, it's working. Nice. So that's the pod. So as you see, it's very similar, but it allows you to keep all the stuff together and save on at least to some extent on typing, because what we also could, for example, have here is a count variable in m, such that we don't need to count how many are in, but just can refer to it. Of course, we could have put all those things into some sort of struct that keeps those variables for us. Those both make plus, and this one makes minus. Yeah, but this way it's yeah, more elegant to have everything inside one object and not just various functions that do things. Any questions? Okay.
Can you just shortly repeat a bit what functions do I want to have in the protected and public and
Private.
sections?
Okay, so public functions can be accessed from anywhere and everywhere. So, for example, like here we are just in some random function and we can access all the public functions. Protected functions are functions which you can only access from either within the object, from within the object which is derived from your object, or if you explicitly specify an object's name or a function name as friend class something my list 2, for example. So you can specify that certain other objects can access your protected functions, but not the rest. And private is pretty much just for your own use, so you cannot access it from other objects.
And the protected function, when I cannot read them into other classes or friend classes, I can only access them in the private section of the class definition.
No, you can access them from anywhere. So like here, we are here in the public area and we are accessing now a protected function.
Yes, but I can only use them in the class definition of this.
No, you can use it in every function that belongs to that class. So if we move these functions out, because that would be more elegant, it would just work just as well. So if we just have the definitions here and our functions there, just need to copy the name of the class. Then it will be then you still can access all the protected functions. That doesn't change anything. But from here, so from the main function, you cannot access anything protected because main is not part of your class. What do you mean? So the functions are defined, you always define functions in your class definition. That doesn't have anything to do with the main function. In the main function, you're just calling your function, the functions that you are allowed to call. It is inside the class because the function is prepended with the class name.
Okay, but without this mark here,
now you could not. But now you would not even belong to it.
it's in the public section.
Hmm?
If this function would be in the public section, then you can access this without the
Yes. Any more questions? Okay, if there are no more questions, then I guess we are done for today. With regard to so the next lecture will be, I think, in 2 weeks, since the next week is some sort of holiday. And the next lecture will already be the last lecture. So yeah, if you have any questions in between, you can write me an email at any time. So if you have troubles with your final project and need some additional guidance, you can write me at any time. Then we can find some time for a short Zoom or something like that, I guess. Or I can maybe answer your questions by email, depending on what the question is. Yeah. So if there are no more questions, I guess I will close the chat for today. And don't hesitate to ask by mail if you need anything.